Good day to all of you. This morning we are going to have a new lesson. The title is Chemical Composition and Systematic Classification of Minerals. The ultimate identity of a mineral is its chemical composition, as many of the physical characteristics that we have learnt in a previous lesson may be common to a number of minerals. Even by their definition, minerals are said to have a characteristic composition, though it can vary between fixed limits. In this lesson, we shall dwell on chemical composition, which is a very firm basis for their study and understanding. It will be cumbersome to study all the existing minerals individually. Classifying minerals into groups with similar characters will bring order and method. This lesson deals with this aspect: their composition, their formulas, formation and occurrence. We shall deal the topic under the following heads: elements and minerals. Number 2, chemical composition and mineral formulas. Number 3, classification of minerals. Number 4, silicate and non-silicate minerals, and number 5, mineral occurrences. When we talk of minerals, we generally mean those that are present in the easily accessible part of the earth called the crust. This thin layer overlying the voluminous mantle, which is mostly homogeneous, consisting of Mg, Fe, Si and O, is heterogeneous in nature. Crust has been rightly described as an oxysphere, since in terms of weight oxygen exceeds over 60%, and in terms of volume it occupies over 90% of the earth's crust. But there is no mineral named oxygen. It has to combine with other elements present in the crust to form a variety of minerals. There are currently 118 elements on the periodic table of elements, of which 98 are naturally occurring, but only 8 of them, oxygen, silicon, aluminum, iron, magnesium, calcium, sodium and potassium, make up 90% of the earth's crust, as seen in the PowerPoint. All of them have abundance more than 1%. We call them major elements. The rest are known as minor and traces. There are some minerals which are composed of just one element. Among metals, elements of the gold group, that is gold, silver and copper, platinum, iron, semi-metal group, arsenic, bismuth, and non-metal group of carbon, diamond and graphite, and sulfur are among the best examples. There are also mineral alloys consisting of two metals, for example, kamacite, iron and nickel, as found in meteorite. More often, however, minerals are composed of two or more elements joined together to form a compound like quartz. Two elements, Si and O. In calcite, consisting of three elements, calcium, carbon and oxygen, and biotite, consisting of many elements including potassium, magnesium, silicon, aluminum, oxygen, hydrogen. Formation of minerals out of the most abundant element is in magma is neither haphazard nor a matter of chance. There are well established principles of crystal chemistry that need to be followed, which cannot be dealt here for want of space and time. Cations, anions and polyatomic ions, which we call radicals, are the building blocks of minerals. They follow a set of patterns in making a mineral which is a balanced electrically and stable thermodynamically. General abundance of cations, anions, atomic and ionic size, charge, coordination number, chemical bonding, electronegativity all play their important roles. However, cardinal principle of mineral chemistry follows what was stated by Pauling in 1960. In a stable structure, the total strength of valency bond that reach an anion from all the neighboring cations is equal to the charge on the anions. This restricts the entry of several cations, though present in the crystallizing magma, to enter a crystal lattice. This is the reason why only magnesium and iron make the first stable structure crystallizing out of a basic magma, that is olivine. When we see that on SiO4 tetrahedra there are 4 negative charges needing 2 divalent cations. These happens to be magnesium and iron, either 2 Mg, 2 Fe or 1 of each. As due to their suitable coordination with oxygen and iron, they contribute the appropriate positive charge to make the olivine structure electrically neutral and thermodynamically stable. This is the working principle in its simplest form, though there are many other factors that are involved in the formation of the silicate minerals. Minor and trace elements normally find their way into the major rock forming minerals by substituting for their major counterparts. Even a tight structure like quartz may have few trace elements as impurities. Olivine will have many more: nickel, chromium, titanium, molybdenum, copper, zinc, etc. Boratite will have many others too, including fluorine, lithium, sodium and barium. Enrichment of minor and trace elements into ore minerals is a special issue. It has been combined general effects, namely processes of magmatism, sedimentation and metamorphism over long geological periods to carve out an ore deposit, which are mixtures of ore minerals and gangue. Native minerals like gold, diamond and sulfur are represented by one symbol only, but it is not so simple for other minerals. Thus it becomes imperative to devise formulas which in a nutshell speak out its chemical composition. With the developments of several high-tech analytical techniques for chemical analysis and X-ray investigations, and detailed chemical composition and atomic structure determination have become routine practices for mineralogists and geochemists. From raw chemical data and X-ray investigations, arriving at a specific formula for a particular mineral is a different subject and shall not be touched here for want of space. However, general comments on chemical formulas of minerals is in order. Most minerals occur as compounds of 2 or 3 elements, cations and anions, or element radical combined. Mineral quartz thus consists of atoms of silicon and 2 of oxygen. Mineral hematite has molecules of iron and 3 of oxygen atoms. When there is no specific number of written after the element, it means there is only one atom of that element present, like in minerals Fluorite, like ZnS. In bonite Cu5 Fes4, there are 5 atoms of copper and 1 atom of iron and 4 of sulfur. Minerals are formed also by the combination of cations and a radical or polyatomic ions, for example, carbonate radical CO3, sulphate radical SO4, chromate radical CrO4, hydroxyl OH among others. Calcite, for example, is formed by the union of Ca and carbonate radical, which itself is the union of carbon and oxygen. Thus, ratio of Ca to C to O in mineral calcite will be 1:1:3. In a chemical formula, radicals are equivalent to any chemical element when put under parenthesis followed by any subscripted number, like in talc. It means there are 2 hydroxyl radicals for each molecule of talc. When there is only one OH radical, there is no need for any subscripted number. For hydrous minerals like gypsum, CaSO4 2H2O, signifies presence of two water, that is H2O molecules for each molecule of CaSO4. Presence of a dot in between CaSO4 and 2H2O means these are two separate molecules and are rationally proportionate. When instead of a number letter n is used, it means amount of water present could be variable, like in formula for opal SiO2 and H2O or montmorillonite. A fundamental difference between hydroxide minerals and hydrous ones need to be clearly understood. Hydroxide minerals cannot strictly be called hydrous, as there is difference between electrically neutral water molecules, that is H2O, and the negatively charged hydroxyl ion OH. The hydroxide ion is firmly held in crystal lattice, whereas water molecules do not possess this property and can replace halogens like chlorine and fluorine in minerals. Empirical and structure formula could be empirical, including only the bulk chemical composition, or structural, giving some idea of the three-dimensional arrangements of atoms in the mineral and their bonding. Currently, only structural formulas are in use. As an example, empirical formula of muscovite is H2KAl3Si3O12, while its structural formula is KAl2AlSi3O10 OHF twice. Structural formula tells that muscovite contains an intricate anionic complex in its structure. Presence of water is as hydroxide and not as H2O, and can be replaced by fluorine anion. Then there are general formulas belonging to one particular group of minerals, which often constitute an isomorphous series, could be represented by a general formula, and then it becomes easy to remember and recognize them quickly. For example, simple group formula for three types of pyroxenes family would be XSiO3. For simpler pyroxenes, where X means Fe, Mg or Ca, and very rarely Mn and Zn. Complex pyroxenes AlSi2O6, where X means Ca, Mg, iron, Al or Fe3, and for alkali pyroxenes X3Si2O6, where X is Na, Li, X3, Fe3Al. Another example could be garnet family, where the general formula is represented by X3Y2SiO4, where X is Ca, ferrous, and iron, magnesium, and or Mn, and Y, chromium, ferric, Mn, Ti, Va or Zr. This can be said for most of the other isomorphous mineral formulas. Coming to atomic variations, some elements can exist in more than one valency state. For example, iron. In certain minerals, both these states of iron are present. In such cases, this is indicated in the formula, like for instance a variety of amphiboles called Rebecite, Na2 Fe3 twice plus Fe2 Si8O22 OH twice. Coming to solid solutions, many mineral series like olivine, pyroxenes, plagioclase, feldspars form solid solutions where more than one intermediate member may exist between two end members. For example, group formula for olivine will be Mg Fe twice SiO4, but for pure Mg olivine the formula will be Mg2 SiO4 and Fe2 SiO4 for pure phthalate. This is best seen in plagioclase feldspar series, which is presented in the PowerPoint. Variable formulas comes next. In nature, 100% chemically pure minerals are hard to find. Quartz and kyanite may reach this purity to certain extent, but several minor and trace elements find entry into most of the minerals by replacing the major cations of the formula. Nickel, chromium, cobalt will be common occurrence in the lattice of olivine by substituting Mg and Fe. In pyroxenes and amphiboles and mica, this is more frequent, but unless the substitution by micro and trace elements is considerable, these elements are not mentioned in the chemical formula. Mineral adamite, which is Zn2ASO4OH, is bound to have copper and cobalt as impurities, but only when copper and cobalt replacement is significant, a variable formula for this mineral will be used as ZnCuCO twice ASO4OH. Fluorite, that is CaF2, normally has very small quantities of cerium and yttrium, but it never reaches significance to represent it by a variable formula. For a systematic study of the vast mineral kingdom, we need to have a pigeonhole system as used in post offices for sorting mail. If we start studying minerals at random, it will be very confusing and time consuming and perhaps a futile exercise. Classification gives order and method to study a large number of things. There can be a number of possible ways to classify the mineral kingdom. In fact, attempts at classifying minerals were on right from 1750 onwards. We can divide them as amorphous and crystallized minerals. The crystallized group can be subdivided into different crystal systems to which they belong. Someone may even like to divide the minerals simply on the basis of their color, but this will not be a satisfactory way, as the same mineral may show different colors. Others might choose to classify them genetically, for instance minerals formed under different geological processes like magmatic, volcanic, Skarn, hydrothermal, sedimentary or metamorphics. Here again a mineral like quartz can originate in more than one way. The most satisfactory classification will be the one which will depend on those characteristics that remain constant. Internal atomic structure and chemical composition thus become the most important and useful basis for classifying minerals. Swedish chemist Berzelius devised such a scheme, traditionally known as Berzelian system of classification, dividing minerals species into major groups according to the nature of anionic group present. In mineral calcite CaCO3, Ca is the cationic group while CO3 is the anionic group. In the mineral olivine Mg2SiO4, Mg is the cationic group and SiO4 is the anionic group. It begins with the simplest, followed by more complex, and culminates with the most complex and important group, the silicate group of minerals, which incidentally make up the bulk of the minerals and rocks of the lithosphere. Each group is then subdivided according to the complexity in internal structure. The following groups of minerals are generally accepted by all with minor modifications and additions. native elements including metals, semi-metals and non-metals. Then sulphites including sulfur is the major anion, includes selenites, tellurites, arsenates and antimonites, sulfur salts, sulfur and a semi-metal as arsenic, bismuth are the anions, includes arsenites, sulf-antimonites and sulfobismuthites. Then comes the halide group containing fluorine and chlorine and bromine and iodine are the anions. Oxides, oxygen is the principal anion which also includes hydroxides containing hydroxyl radical as an anion. Then comes the wide list of oxygen salts which includes carbonates, borates, sulphates, phosphates, chromates, followed by arsenates, that is ASO4, vanadates, tungstates, that is WO4, molybdates, MOO4 and urinates and tellurates. Silicates are the backbone of all the mineral kingdom. This can be included among oxygen salts, but deserves a special group where silicate group, that is SiO4, acts as an anion combined with other elements and includes silica. Some of the most common mineral groups and their compositions are presented in the PowerPoint. In today's lesson, we have dealt with 3 modules, namely elements and minerals, chemical composition and mineral formulas, and 3 classification of minerals. The remaining 2 modules we shall continue in the next episode, where we shall discuss silicates and non-silicate minerals and mineral occurrences. Hope this has given you some idea as to the mineral, their composition, their formulas and their classification. Thank you very much.